You're drifting in space, weightless and silent. Ahead of you is a perfect, dark circle carved out of reality itself, bending light around it like a warped lens. And naturally, as you stare into that dark circle, the question creeps in: can you actually fall into a black hole and survive? The first step to finding out is leaving behind the myth that black holes act like cosmic vacuum cleaners. From a safe distance, they behave exactly like normal stars. If our sun were magically replaced by a black hole of the exact same mass, Earth would continue orbiting exactly as it does right now. Closer in, the danger stems from the uneven way gravity acts on your body. Looking at this diagram, you can see how this unevenness works, a difference in gravitational pull called a tidal force. Because your feet are closer to the massive object, they experience a stronger pull, mapped by the noticeably longer force arrow. That means surviving an approach has nothing to do with fighting gravity. It requires finding a black hole with a highly specific type of tidal force. The stakes shift from if the fall is fatal to where exactly you decide to take the plunge. Let's start with the lethal scenario, a small, stellar mass black hole, roughly the mass of our sun. Here, a tight gravity gradient ramps up tidal forces so fast the object stretches vertically and squeezes horizontally. As particles break apart, you witness an atomic-level dismantling, spaghettification. There is no coming back. To survive the journey, we have to look away from these small anomalies and point ourselves toward the supermassive black holes found at the centers of galaxies. This animated curve illustrates why giants are safer. A small mass has a steep gravity gradient, but a supermassive black hole spreads its immense mass over a vast area, flattening the curve. The gravitational difference between your head and feet becomes imperceptible at the boundary. That sheer scale acts as a biological shield. The most massive objects in the universe are only survivable if they are unimaginably large. Approaching one of these giants brings you to the event horizon, the absolute point of no return, where not even light can escape the inward pull. From the outside, this looks like a terrifying threshold. But from your perspective, falling in, the crossing is completely silent. There is no flash, no shockwave, and no sudden barrier. You simply pass right through, which creates a bizarre reality. For a brief window of time, you are fully alive and physically intact inside a black hole. But if a friend is watching your descent from a safe distance outside, they see a completely different sequence of events. This dual pane visualizes the split. On the left, your perspective, crossing the boundary at a constant speed. On the right, the observer sees gravity trap your light. You exponentially slow down, freezing on the threshold line, fading into a reddened ghost. To the rest of the universe, you are frozen forever at the edge. But to yourself, you are actively descending deeper inward in real time. Back inside the event horizon, that real-time descent continues, but space here functions like a relentless one-way waterfall. As this grid illustrates, the very geometry of space now tilts entirely toward the center. Every single directional vector points to one central dot. Swimming against the current is physically impossible because there are no paths leading outward. All of those paths lead to a single destination at the absolute center, the singularity, a point of infinite density. At this exact coordinate, the established rules of physics stop working. Our current understanding of gravity, quantum mechanics, and space-time completely breaks down. While you survived the initial fall and crossed the boundary unscathed, reaching the singularity guarantees a fatal conclusion. Your survival was strictly temporary. Yet, through mathematics and observation, we have managed to calculate every step of this journey, predicting the stretching of atoms and the slowing of time inside a space we can never actually see. By mapping these inescapable regions, we have found clear answers in a place where no traveler can ever return to describe.